Hey, it's Michael. Welcome to part two of a tutorial covering how to implement a DDR3L SDRAM interface in a single I/O bank in a 7 series Xilinx FPGA. This side's going to move beyond implementation and into testing that SDRAM. Uh, why would you want to do that, one would ask? You're the FPGA guy. Doesn't the board level guy do that? Well, let's just say that you're working on a team and you're the FPGA guy, and there's a board guy, and there's a tech lead guy, and so forth. And you've gone ahead and said, hey, here's the pin assignments. And by the way, I need a 100 megahertz clock because that's what Xilinx is recommending. And you're told, hey, no, I can't give you 100 megahertz. I can only give you 25. So, okay, well, yeah. So you implement it with a 25 megahertz clock, which you boost up to 100. Oh, what happened there? My camera fell. You boost that up to 100. You feed that into your memory interface generator, your SDRAM controller here, and you have everything working and on a development board, and you're okay. The board comes in, you give the hardware guys your files to program the FPGA, and you get a call. It doesn't work. Well, and so what you do is you break out your little test image and your little Vitis project that takes a peek at the status signals here, MMCM locked and it calibration complete and so forth. And what you find is your MMCM isn't locked and your init calibration complete is not complete, deasserted and so forth. You go, what? It all worked in my development board. What happened? And so you ask for the schematic because you've got a schematic that's a few months old. And lo and behold, you found that your 25 megahertz clock had become a 100 megahertz clock because somebody else had read the documentation. And so you go ahead and you redo the FPGA image to use the 100 megahertz clock instead of a 25, and you get everything working. And you do that with a small targeted test image and a small application that allows you to take a peek at these status signals and to run a little test on the SDRAM. So in part one, we covered not generating the block design, but generating the SDRAM controller, using this memory interface generator wizard and so forth. We went ahead and generated the bit file, we exported the XSA, we generated a pin list, and now we're ready to jump into the Vitis side of the project. So I'll go ahead and close with Auto. And here we are in our Vitis folder underneath our project hierarchy, and there's the XSA file we've generated. Now I've gone ahead and I've cheated a bit. We could do this all in Vitis, but this accelerates things a little bit. I've got a little tickle script, and I didn't write this tickle script myself. I inherited it from somebody, and I've tweaked it. But what does that tickle script do? It's going to generate the application that's running on the microblaze. It's going to go ahead and check to see if that XSA exists. If it does, I'll go ahead and clean out a bunch of stuff because Vitis doesn't like to overwrite existing folders, so I'll go ahead and delete them so we get a clean start. And then I'm going to go ahead and create the platform from the XSA file. And this is where in the previous part we discussed the need to know the instance name of the microblaze. And there it is, host CPU. We need to know that instance name because we could have multiple instances of a microblaze microcontroller in our design. But this is the application or platform we're creating for this specific instance. There's a bunch of defaults here. By default, it will create the whole Hello World application, and by default, it will put that application into the local memory bus block RAM, so the internal RAM. So I don't have to specify that. Those are defaults. I could specify them, but I didn't. All right, then I go ahead and activate that. I generate that platform. And the next thing I do, here's where we go ahead and generate the Hello World application. So we're creating an application with that name based on that platform which we've generated up here. Standalone domain, meaning there's no operating system. We're not using Petalinux. We're not using FreeRTOS. This is just bare metal. And not here, but by default, it's going to generate the Hello World application and target it to run out of internal memory. The next thing I do is delete the whole Hello World.c file that has the main.c in it. And then I import my sources, my own sources. And they're up here in the just one level up. If I can go one level up, they're right there. There's my C source files. The main thing being I have a main, and that main invokes, I just called it LED test, but it invokes an application that's going to put up a little command line interface and allow me to invoke a few functions with just a press of a single key. Okay, so let's go back to the Vitis folder. I'm going to, I could invoke or source the stickle script from within Vitis, but instead I'm just going to double click on this batch file. And this batch file sets up a number of things. One is opening up a command window, and this settings.64 bat is provided with every Xilinx install. This is the install for 2022.1. Within that, I'm going to run xsct, and then I'm going to source or run that tickle script that I've just shown you. So here we go. Double click on that. A whole bunch of things are going to happen. It's going to create that platform, and then it's going to create the application and swap out hello world.c for the main.c that I have up in my C sources folder. This doesn't take long. Here we go, generating the board support package, which is part of the platform, and then generating the application. And so I can see I have my platform and I have the application. And now I'm going to go ahead and open up Vitis so that I can drive this from the GUI here. I've already got the A7 board hooked up to a USB cable so that I can talk to it. And there we go. Just for good measure, I'm going to go ahead and build my application. It should already be built, but I'll build it again. And then I'm going to go ahead and run it. Run, launch hardware. I can close this. And because I put a Microblaze debug module into the block design, along with checking the use JTAG UART, I'm now communicating with my command line interface through JTAG. So this is, I'm not using the UART interface on the ARDI board into the FPGA. I'm just going straight through JTAG. And so there's the little command line interface that my my application puts up. And why is it reloading? Who knows? But this is the display menu that we're looking at. Puts up main menu, and if I press 0, I get the version. 1 dumps some registers and so forth. 2 reads the user access value, which is a timestamp that's put into the bit file. 3 dumps the first so many words of SDRAM, and F runs this SDRAM test. So let's have a look at this SDRAM test, which is function F. Function F. There it is, memtest. Memtest is very simple. It points to the start address of SDRAM, sets up a data value of that, and then it goes ahead and just writes to whatever parameterized number of words, incrementing the data value by that on each iteration. And then it goes and reads it all back and compares what it's written. Very simple test. By no means thorough, but good enough. So let's have a look. Let's go back to our Vitis command line interface. And I'll go ahead and do an SDRAM dump to start. So I'm going to type 3. And I'm dumping the first few words of SDRAM. Now, I could go back and tell you how I found that address using xparameters.h, but that's another tutorial. And what I notice is it's not all random data here. So that SDRAM calibration did something. It wrote a pattern to these first few words of SDRAM in order to do its calibration. So this looks like random data here. Let's go ahead and run the SDRAM test. So I'm going to go ahead and hit F. Off it goes. We started at the base address. We wrote it's beyond 64K. I don't even know, maybe 256K words. It wrote that pattern to and read it back. Everything compared, all good. Let's go ahead and dump SDRAM again. And I'll scroll back up to the beginning, and you can see there's that first word, second word, so that first word, simple count pattern here, 1, 2, 3, 4, 5, 2, 3, 4, 5, 6, and so forth. And that's all there is to it. So I've been able to prove that my SDRAM is working using a minimal block design, a minimal FPGA project, a small Vitis project. I'll go ahead and show the board again. And in the previous portion of this tutorial, I don't think we can see it, but I went ahead and attached the MMCM locked and the init calibration complete signals to LEDs. I don't think we can see, but they're lit up, so they're both high, both asserted. So we're locked and the calibration completed. And then I tied the 100 megahertz clock. Maybe that light's too bright. I tied the 100 megahertz clock to a divider so it would blink. I don't think we can see that, but this gives me confidence that the logic in the FPGA is working and the SDRAM interface is working. And so now I can confidently hand at least that portion of the project off to the hardware guys and the software guys and say, go to it. Looks like it's working to me. All right, I hope that helped. Take care, and let me know if I can do a better job next time. Catch you.